Continuing our quest to describe motion, today we're going to look at acceleration. So what are we learning? We're going to learn what is acceleration, what units we're going to use, and what the equation for acceleration is. And we're going to look at the difference between average acceleration and instantaneous acceleration. So a car moving to the right changes its velocity from some initial time to some final time. When you press on the gas pedal or the accelerator pedal, the car speeds up. The changing of an object's velocity with time is called the acceleration. Acceleration is a vector quantity. In this case, the acceleration is positive. We will define acceleration as the change of velocity over the change in time. It is what we call a rate. It is the rate of change of velocity. When we say rate, basically that means we're dividing something by time. And notice that we are using delta V here. As we've seen this before, that translates into the final minus the initial velocity. And of course, we've seen this before. Delta T is the final time minus the initial time. When you press on the brake pedal, the car slows down. Again, acceleration is a vector quantity. In this case, the acceleration is going to be negative. Here, the initial velocity is in the opposite direction of the acceleration. So the object is slowing down. You want to be careful in your thinking about acceleration. There's two main ways. First, remember that acceleration is not velocity. It's the rate of change of velocity. Also, negative acceleration does not always mean that the object is slowing down. Sometimes it does, sometimes it doesn't. Acceleration is the changing of an object's velocity with time, and the rate change of velocity. Since velocity is a vector quantity, it has magnitude and direction, and here is the wall of death example. She is driving her motorcycle at a constant speed, but she is changing the direction. She's going in a circle. And actually, in this case, the acceleration vector is going to be pointing towards the center of that circle. Now, this is two-dimensional motion, and we're going to look at this in great detail later. But what I want you to take away from this is that acceleration can be speeding up. Acceleration can be slowing down. Acceleration can be changing direction. Often when we say slowing down, you've heard the term deceleration, and we won't use that here. These are all acceleration. What are the units we'll be using for acceleration? Well, here's our equation, and we're going to use meters per second squared. Now, what in the world does that mean? Well, up here at the top we have velocity, and the units for that velocity are meters per second. On the bottom we have time. The unit for time is seconds. So now we have this compound fraction. We can rewrite it like this. If you divide by s, it is the same as multiplying by 1 over s. Now we have two fractions that we're going to multiply together. All we have to do is multiply through the top and multiply through the bottom, and we get our answer of meters over second squared. So there's a couple ways we can say this, and here's what it means. Meters per second per second. So it is a change in velocity in meters per second. But usually we just say meters per second squared. Now let's try out our new equation. So let's say, for example, our car speeds up from 10 meters per second to 20 meters per second, and we go 2 seconds to take it to do that change in velocity. Well, let's plug that into our equation. Our change in velocity up here will be 20 final minus 10 initial. And then on the bottom, it's just 2 seconds minus 0 seconds, and we get positive 5 meters per second per second. Now, what does that mean? An average acceleration of positive 5 meters per second squares, that means, on average, the car changes its velocity by positive 5 meters per second every 1 second in the positive direction. Here's our acceleration vector. It is in the positive direction. What if our car is slowing down? Again, acceleration is a vector quantity. Let's go to this example. Let's say the car initially is going 20 meters per second, and then 2 seconds later it's going 10, sort of the opposite of what we saw before. Plug that into our equation here, and now we come up with a negative number. Acceleration is a vector quantity, meaning that our vector for acceleration will be going in the negative direction. And here it is. Now, what does this mean? What does negative 5 meters per second squared mean? If this is an average acceleration, it means that the car is going to change its velocity by negative 5 meters per second every 1 second. So a few things to remember here. If velocity and acceleration are in the same direction, it will be speeding up with time. If the velocity and acceleration are in opposite directions, you will notice that it's going to be slowing down. As you can imagine, the value of the average acceleration is often different for different time intervals, so it's useful to define instantaneous acceleration, which is analogous to the instantaneous velocity. The instantaneous acceleration is the limit of the average acceleration as the time interval goes to 0, or it gets closer and closer and closer and closer to 0. It doesn't ever get there. Our units are the same. This is the acceleration at any given instant using a very, very small time interval. All right, let's take a look at what we know so far. Our average acceleration is the change in velocity over the change in time. Our units are meters per second squared, or meters per second per second. The difference between average and instantaneous is that the instantaneous, well, is the acceleration at any given instant. And all that means is that we take our same equation and we try to make that delta t, or that time interval, as tiny as possible. Same units as average acceleration. All right, complete your Cornell notes, rewind and review as necessary.